So in thermochemistry, we're studying the changes in energy involved in these chemical reactions, such as hydrogen and oxygen combined together to give us water, and some amount of energy. Energy is being evolved in that. And so thermodynamics is the study of energy and its transformations. Energy and its transformations. And you may have heard of the laws of thermodynamics. People that are engineering, they like to talk about the law. There's the first law of thermodynamics, and the second law, and the third. There's these laws of thermodynamics. And I never studied law, so I'm not really big on that, but I do pay attention anyway to thermodynamics, energy being gained or lost in systems. Okay, so what we're going to do here is we're going to take a look at what we define as a system. Now, it gets a little complicated in that we have this entire universe, and when we want to look at a chemical reaction, we should take into account the entire universe, but it's not really practical. So if I want to do a chemical reaction inside of a test tube here, I have to keep in mind that there's a whole universe out here, and that universe is adding a little bit of heat energy. There's a little bit of electromagnetic radiation coming in here. I should pay attention to that, but I'm probably not. Is anybody here taking physics? A couple of people have taken physics. You know, like 99% of physics problems, they just ignore friction. It's like it's just not a thing. Like, okay, there's a question like, okay, there's a box. How much energy does it take to overcome the coefficient of friction here? Yeah, but beyond that, okay, you shoot a bullet and the bullet's traveling through the air. Do they account for the friction in the air? No. They just assume it's going through a vacuum. Yeah, he's like, wait a minute. Everything I learned in physics is wrong. Well, we won't quibble, okay? So we need to separate what's happening. And so what we do is we try to define what is our system. And so our system is going to be what it is that we're actually studying, the thing that we're looking at. So I'm going to go like this here and say this here is my system. Okay, so my system is the thing that I'm looking at. My system is the thing that I'm looking at, the thing that I'm focused on. Now, sometimes energy leaves a system. So if we have energy leaving a system, and I'm just going to say energy is just an E with an arrow on the top because I'm lazy. So that's energy leaving the system. We would call this exothermic. Exo meaning it's exiting, thermic meaning heat, so heat leaving the system. And we could have energy entering the system. That could happen too. And what would we call this then if it's energy going into the system? Endothermic. Endothermic. Now, we have symbols for this, and our symbol is kind of a cursive Q. And we refer to this here as the enthalpy, or you might just think of it as the energy or the heat. And we kind of think of these as all being synonymous. They're not really, and people will fight over that, but really we're just thinking of the energy. And if energy is leaving a system, mathematically, we call this negative. And if it's entering a system, or if it's being added to a system, we make it positive. So if you're adding energy to something, it's positive. If you're removing energy, it's negative. And that's important because we're going to do some math, and we're going to be adding some numbers, and we're going to be subtracting some numbers. So if it's exothermic, it's a negative sign. Now, if something is exothermic, how does it feel? Like if something is exothermic and you put your hand next to it, does it feel warm or cold? Warm, right? Because it's giving off heat. So exothermic will feel warm, whereas endothermic will feel cold. Will feel cold. Okay. Now these systems, we have different types of systems. We have isolated, closed, and open systems. Now our isolated system this is a system where it's like a thermos bottle. So a thermos bottle like this is something that you might put your Starbucks in, and if it is perfect, iso means it doesn't change. That means we do not lose, so no loss of heat or mass. So we don't lose heat energy out of this, and we don't lose any of our coffee. Now that's in a perfect ideal world. Like if you could have a perfect isolated system, you could fill your coffee mug up, or excuse me, your thermos here up in 1974 and open it up today, and you'd have nice hot coffee. Now we know that's not realistic. So we aspire to an isolated system. It's not really practical. We've not really achieved that. We do the best we can. Now a closed system would be like if you have your Starbucks cup here and it has a lid on the top. It's got a lid there. Okay, so this is closed. A closed system. Now in our closed system, we will lose heat. So heat is lost. So lose heat, but we do not lose mass. So heat will be evolved from this. It will feel warm. Heat energy comes out and eventually cools down. But we don't spill any of our coffee. I should totally get a kickback from Starbucks. They should be giving me money for this. Every time I mention Starbucks, that Starbucks, you know, and it has that symbol, that's Starbucks, there should be like a ka-ching, 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 right? Well, I think so. Okay. And then the last one here would be an open system. Now, an open system would be like if you have a bowl here of porridge, and in our porridge here, we're losing heat, and stuff can escape here. So we can lose heat and mass. We can lose heat and mass. Both of those can be lost in an open system. Ideally, when we're doing our chemistry and our experiments, we have an isolated system, but that's not really practical. We definitely don't want an open system. It's hard to measure things like how much energy or heat is in something if stuff is escaping. Okay, that makes the math really difficult to do. So we try to keep it as closed as possible. All right. Now, let's try an actual example here. So, burning gummy bears. I love gummy bears. Don't you like gummy bears? Gummy bears are awesome. They're just cool, they're cute, and they're delicious. So here's a thermochemical equation, and it gives us some fancy symbology here. All right, so we'll try to define what's going on here. So we have here some sucrose. So C12H22O11 plus 12O2 reacts with oxygen here. Let's see, it gives us 12 carbon dioxide and 11 H2Os. Okay. And it tells us that one trip through this gives us a change in our enthalpy of reaction here of some number. It's a negative 5645 kilojoules per mole. Now, I just threw some big words here out. Okay, delta means change. This R here means reaction. Because I'm too lazy to write the whole word reaction, I put an R. And then when I try to explain what it is, I'm still too lazy and I just say RXN. But it just means reaction. And then H here, and the little degree symbol there. That just means the energy as far as we're concerned. And that little thing up here, that little symbol, the degree symbol means at STP, standard temperatures and pressures. In other words, basically, we'll just say room temperature. I mean, really, I think it's 0 degrees Celsius and at sea level, but we're not going to fight over it. That's all that stuff means. Now, if you forget all of that, that's fine. Okay, what you need to know is over here. Here we have that negative sign. That negative sign tells us it's exothermic. It's exothermic, right? It's giving off heat energy. We are taking sugar, we're combusting it, and we're producing energy. It's an exothermic reaction. That's what we need to know. So the question is, how much energy is transferred as heat by burning 10 grams of sugar? Okay, so I'm going to take my 10.0 grams of sucrose. I'm just going to say sucrose, SU, because I'm too lazy to write C12H22O11. And I'm going to convert that into moles. So if I add up 12 carbons, 22 hydrogens, 11 oxygens, that's 342.3 grams of sucrose per mole of sucrose. And here we have a mole of sucrose. A mole of sucrose is 5645, negative 5645 kilojoules. Kilojoules are just units of energy. So then if I do my math on this, my sucroses here should cancel out and I'm left with my kilojoules. Now I've predicted it should be negative. This is giving off energy. And when I did the math on this, I ended up with a negative 163 kilojoules of energy. It's exothermic. So, if I burn a gummy bear, should it feel warm? Yeah, it should feel warm. Okay. I want to figure out how much energy is in a gummy bear. So, does anybody have goggles? Do you have goggles? I need a pair of goggles. I need to demonstrate good, yeah, could you? Thank you. All right, thank you very much for helping me here. Okay. Because, you know, if we record this and it's out on the internet and I'm not wearing goggles, that looks bad. Okay. All right, so what I'm going to do here is I'm going to ignite my gummy bear, but to get me started here, I've got a Bunsen burner. And I'll light that on fire. Now, if you do it correctly, a Bunsen burner should have a blue flame. If you have a yellow flame, you're doing something wrong. And the inner blue cone here, the inner blue cone, just at the top of that is the hottest part of the flame. Now, I can take the gummy bear and I could swallow it, and then I'd say, okay, measure the change in energy. That's difficult. That's a challenging thing to do because I'm a big system. But here I have a small system. I've got a small system. So I'm going to burn my little gummy bear in my small system. But, you know, just, they're not very combustible. But if you have magic juice, magic powder here, I'm going to combust it. So what I have here is some potassium chlorate. I call it magic sauce, but it's potassium chlorate. I'm going to heat it up here. And as it heats up, it decomposes into potassium, potassium chloride and oxygen. And oxygen, as we learned, hopefully we remember, is a strong oxidizing agent. Oxidation, reduction. Remember that? Remember those words? Okay. So I'm going to take this, I'm going to drop it in here. Now, it's almost a liquid here. If you want to film this, this is kind of a fun one. You know, whip out your cameras here. Okay, here we go. Are you ready? Get it on video. Let me know if you're ready. Okay, we're good to go? All right, so I'm just going to take my little gummy bear here, and we're going to sacrifice Mr. Gummy to the gods of science. No, I don't want to be sacrificed. Yes, you should be sacrificed. It's for science, but I don't like science. Okay. Thank you. Now, if I put my hands over here, oh yeah, that I feel heat. There's definitely heat coming off of that. That is exothermic. Okay. Now, it's a good thing that when you eat a gummy bear, all that energy doesn't get released at once, because you might spontaneously combust. That's a lot of energy. That was one gummy bear. That was only one. And who eats just one? So, biology people, why is it when you eat a gummy bear you do not spontaneously combust? Why doesn't that happen? So you have these things in your body called enzymes. And enzymes help this reaction happen, but a lot slower. It's a nice, slow, controlled reaction. So you get the same energy, it's just spread out over a longer period of time. Because if it all happened at once, poof, you'd be gone. Okay, so your body tries to control these reactions with enzymes, tries to do it nice and slow. But gosh, it's a lot more fun when you can make it go like that. Okay. Okay. All right, so we have some terms here and some vocabulary. So heat capacity. Dun, dun, dun. Heat capacity. So the heat capacity. The heat capacity is the amount of energy it takes to raise the temperature of an object by 1 degree Celsius. So say energy needed to raise temp by 1 degree Celsius. Okay, so that's the whole object. To raise the whole object by 1 degree Celsius. Now, depending on the mass of the object, it's going to change the heat capacity. Like Lake Superior is huge. It has a huge mass. It's going to take a lot of energy to raise the temperature of Lake Superior by 1 degree Celsius, as opposed to a little cup of cocoa. A little cup of cocoa has a very small heat capacity. It takes much less energy to raise this. And so when I say this to people, there's more heat capacity in Lake Superior than there is in a cup of cocoa. People will be like, yeah, but Lake Superior is colder. Yeah, but that doesn't matter. It's the size, it's the mass that makes the difference. Okay, so heat capacity is the amount of energy to change the temperature by 1 degree. And we have a formula for this, where we say that our enthalpy, or our heat here, is equal to the heat capacity times the change in temperature. And there's no units for mass in that. There's no units for mass. Now the molar heat capacity P-A-C-I-T-Y, capacity. Okay, the molar heat capacity, this is the energy required to raise 1 mole of a substance. So we'll say energy to raise temp of 1 mole 1 degree Celsius. So 1 mole of a substance to raise it 1 degree Celsius, how much energy it takes to do that. And our equation for this is going to be very similar. We're going to have our enthalpy here is equal to N. N is our number of moles times the heat capacity times the change in temperature. And then the one that is used most often, the one that I personally prefer, is our specific heat. So the difference here, this is mass here. Okay, that's not moles. Mass, and that's in grams. And this here is moles. Is moles. Even though M, mass, or moles starts with M, but so does mass. Okay. All right, now we can go back and forth. If you're given the moles, you can convert moles into grams. You've done that before, converted moles into grams. And you've also converted grams into moles. All right, so you could go back and forth. This is just the one that gets used a little more commonly. Now, sometimes, just to confuse us, there is something called a specific heat capacity. And that's confusing because if it's specific heat capacity, we see the specific in multiple places, right? And I hate that. I hate it when people do that. And that gets frustrating. Okay, so I'm going to try not to do that, but sometimes we see that out there just to mess with us. But specific heat is what we can do. Now, different things have different specific heats. And so this is just a table in your textbook. It shows us that different things have different specific heats. And so if we take a look at water, does it give us a value here for water? Water at 25 degrees is 4.18. Okay, so that's a good number to remember. So the specific heat, the C sub S of H2O, is equal to 4.18. Does it only say 18? Yeah, it's 184. Joules per gram degree Celsius. That's how much energy it takes to raise 1 gram of water by 1 degree Celsius. The more mass you have, the more energy it takes. So, for example, if you have 3 bowls of porridge, small, medium, and large, which bowl has the largest heat capacity? The big bowl. The big bowl has a big heat capacity. The small bowl would have the smallest. Therefore, if you were to set them out, which one should cool off the quickest? The small bowl, right? The small bowl should be the cold one. The big bowl would be the warmest one. The medium bowl should be in between, right? So Goldilocks and the 3 bears goes against the laws of thermodynamics. Remember that the next time you tell the story. Make it scientifically accurate. Say, I know, the traditional story says that the baby bear bowl is the one that's just right. But that goes against the laws of thermodynamics. It should be the medium bowl, right? So get it right. Because in this house, we follow the laws of thermodynamics. Okay. All right, so an actual problem here, a sample type problem. My wife and I were getting engaged. She said, ooh, let's go get a ring. I said, okay, let's go get a ring. And so we go to the ring store, and the rings, I don't know if you all know this, but they get expensive really quick. And I'm a teacher, I don't have any money, right? So I'm kind of freaking out over this. And so anyway, I have a conversation with the person selling the rings behind the counter, and I'm like, do you have anything cheaper, like not like super expensive? And the dude was really smooth because he's like, yeah, but you can't put a price on love, right? Isn't she priceless? And I'm like, I can put a price on love. I know exactly how much love I can afford, right? I know what my credit score is. Okay. So if we have a 10-gram ring, so a 10-gram engagement ring here, give us our equation here. Okay, so I've got our enthalpy is equal to mc sub s delta T. Okay, and I've got, let's see, some numbers here, I've got a mass of 10 grams. So 10.0 grams. And then my change in temperature tells me is 12 degrees Celsius. And the amount of energy that is evolved here, it takes 46.2 joules. Okay, and then what I'm solving for here is the specific heat. I'm going to compare it to the specific heats of these other materials to see what this ring is made out of. It's a good thing my wife doesn't know thermodynamics. Okay, but, so we're just going to take this equation and solve for C sub S. So C sub S is equal to here Q divided by mass delta T. Okay, like that. And I can plug some numbers in there. I've got 46.2 joules divided by 10.0 grams. And my change in temperature is 12 degrees Celsius. Okay. And when I do this, I get some number. If anybody's got one of those fancy calculating devices, figure out what this ring's made out of. Yeah, it's copper, isn't it? It's 0.385-ish. Yeah, you were right. You're absolutely right. I'm sorry if I disparaged your calculating there, but yeah, I'm a cheapskate. But so this is the wife. This was on a date night. There was a James Bond movie that came out. This is a few years ago. And so we got dressed up. I dressed up like James Bond, and she got a nice dress on. And we went to go to the movie theater, and it was just kind of fun. It was kind of a date night thing because we're kind of geeky like that. So anyway, that's her copper ring there. But you know, if you polish it up really good, we can take these equations. We can take this equation here, this equation, and make it equal to itself. So for example, we could say that the amount of energy that is lost from one system is equal to the amount of energy that's gained in something else. So for example, when I had my gummy bear in here, this was exothermic. The energy that was lost here went out into the universe. So the energy lost was equal to the energy that went out into the universe, right? And so we would say that what's lost has a negative sign because it's exothermic, it's losing energy. And what's gained is positive, that's endothermic. So like the universe is absorbing that energy. All right. So I'm just going to leave it at that. Now what we'll do is the next time we get together is I'll give you some examples of how that works.